So we have the water waves. Water waves, that is the first example of transverse waves. Okay, then we can talk about all electromagnetic waves. Electromagnetic. All electromagnetic waves. So when I talk of electromagnetic waves, I mean the light waves. Light wave, that is visible light. Then I am referring to radio waves. Radio waves. I'm referring to microwaves. Microwaves. I'm referring to infrared waves or radiations. I'm referring to UV or ultraviolet. Ultraviolet. Ultraviolet waves. I'm also referring to what we call the X-rays. And finally, I'm referring to what we call the gamma rays. Gamma rays. So if somebody asks for 3 examples of transverse waves, you can go and break these electromagnetic waves and then list them separately. We talk about the light waves, the radio waves. All these ones are transverse. You remember in our differences between mechanical and electromagnetic, we said electromagnetic are only transverse. The meaning of transverse, we have explained it. Vibration of the particle, okay, is perpendicular to the direction of travel of the wave. Then, what about longitudinal waves? Let's talk about longitudinal waves immediately after the break. We'll be back from the break. This teacher SULAIT, still taking you through the concept of waves. Now, let us look at what we call the longitudinal waves. Remember, we are still looking at types of progressive waves. A wave, which is as a result of continuous disturbance. We have so far looked at the transverse, now we are on longitudinal. People who are making notes, hope your notes are flowing very, very well. Now we need to define what is called longitudinal wave. Dear viewers and my class students, what are longitudinal waves? Oh, tell me. So we are going to discover that these longitudinal waves, or a longitudinal wave, is a wave, or is the one where the particles of the medium vibrate in the direction parallel to that of wave travel. We are going to demonstrate this. Oh, this is a wave where particles is a wave where particles of the medium vibrate in a direction or in a direction parallel. This is now a very, very important word. Parallel to that of wave travel. So in this kind of arrangement, particles do not vibrate perpendicularly, like in the case of transverse. Here, particles are vibrating parallel. For example, my sound waves. When I set molecules around my mouth to vibrate, they are going to be vibrating parallel to the direction, because I need my sound to go to this direction. So particles, they will vibrate, particles of the medium. So the medium which is here, it is air. So particles of air, which air is invisible, God gave it to us for free, is vibrating. Okay, the particles in air vibrate in the direction of travel of the wave. What I'm trying to mean is this. If we can get an illustration, assuming this is the direction of travel of a wave. So particles of the medium, this is how they are going to behave. they are going to contract or to compress themselves and then finally form what we call rarefactions. So you will find particles in this kind of arrangement. This is their nature, okay? And then after a particular, distance, they come and compress. They come and compress. Then again, they go back and give rarefactions. And then finally, they come and compress. That's what is going to happen. So this is the region R, this is region C, this is R, this is C. R means rarefactions. Rarefactions. Then C are what we call the compressions. Those are the compressions. So a longitudinal wave travels in form of rarefactions and then compressions. Don't forget that this is direction of travel of the wave. Direction of wave travel. Direction of wave travel. So now this takes us to the meaning of rarefactions. We are going to see that a rarefaction or rarefaction, these are regions, or if it is a rarefaction, is a region in which oscillating particles are far apart. You can note that one down. That rarefactions of a longitudinal waves, rarefactions, or a rarefaction is a region in a longitudinal or on a longitudinal wave, or a region of a longitudinal wave, of a longitudinal wave, in which oscillating particles are far apart. So the oscillating particles we are talking about are these and these. These are oscillating particles. These are oscillating particles. Even these ones are also oscillating particles. What about compressions? So the opposite is true for compression. Where now are close together, where particles are close together, those are compressions. Okay? So a compression is a region, or these are regions of a longitudinal wave, longitudinal wave, in which oscillating particles. I told you one oscillation is a to and fro movement of a particle, in which oscillating particles are close together. They are close each other, or close together. They are close together. Now we are going to see there is a special name given to two consecutive or two adjacent rarefactions. Two successive compressions or two successive rarefactions are going to form something which is very important in our wave motion. And we are going to see this term under the terms used in wave motion. But before we go to the terms used in wave motion, we have already stated some terms, rarefactions, compression, but these ones only apply to longitudinal. Then we are going to see also specific terms for a transverse wave. Now let us look at some of the examples of longitudinal waves. Examples of longitudinal waves. So dear viewers, what are some of these examples of longitudinal waves? Oh, people have seen compressions, now they are thinking of the compressional spring waves. Very good. So that is the first example. Compressional spring waves. Good. Then the ultrasonic waves are also going to fall here. But we cannot mention ultrasonic without talking about sound waves. So sound waves, the first example, by the way. And also, I don't know whether you have ever compressed a spring. It goes and spreads, and then you see some, rarefactions. And then finally you see congested, particles. When the particles of the spring are congested, okay, and then finally it spreads. That movement is what we are talking about as longitudinal. Whatever we are talking about in physics is not abstract. It is something which we experience in our daily lives. So, sound waves, then talk about, lastly, the ultrasonic waves. Okay. Now, this takes us to the terms used in wave motion. I've been hiding away from these terms, but now it is high time to talk about them. We shall see where a given term applies. If we have wavelength, for example, as a term, how do we define it in a case of a transverse wave? In case of a general wave, if you're talking about general, any wave, what is wavelength? What about if somebody tells you to define wavelength as applied to a transverse wave? Are you in a position? What if he tells you to define wavelength as a term used in waves as applied to longitudinal? That's what we are coming back for immediately after a break. Yes, my dear viewers, you are welcome to another interesting episode, and that is the terms used in wave motion. So, the first term we are going to talk about is what we call amplitude. Can everybody say amplitude? Amplitude. Amplitude. Oh, you are saying it well, but now what is amplitude? Oh, we are going to see that if there is a disturbance in a medium, a particular particle in a wave can be displaced to its maximum position. Okay? So the maximum displacement of a particle in a wave from its rest position, from its equilibrium position, from its fixed position where it was fixed before the disturbance is what we are talking about as amplitude. So amplitude is the maximum displacement of a particle in a wave from its rest position. Let us take an example of a transverse wave. In a transverse wave, assuming you have a transverse wave, this is its displacement. Displacement in meters, then against time. And you have got something of such a nature. Okay, something of such a nature. So what we are referring to as amplitude, a particle, this is the rest position. A particle at this point, at this position, is resting. Okay? So if a particle is displaced maximally, we shall go and look at this displacement. We measure it from the vertical axis. So this is what we call the amplitude. Amplitude A. Okay? Also, it is the same for the regions below the rest position. These are regions above rest position, and then these are regions below the rest position. So this is also amplitude. So amplitude. This is also amplitude. So A is equal to amplitude. Amplitude. So here we have defined amplitude in reference to a transverse wave in which particles are in which particles they are vibrating or oscillating perpendicular to the direction of travel of the wave. Okay, dear viewers. Now let us look at a crest on a wave, a crest. Oh, now we are going to see for a transverse wave, this works on only a transverse wave. We are going to see that a crest is a point of maximum displacement above the rest position. This is the maximum displacement above the rest position. A point of maximum. So the whole of this is a crest. A crest. This is a crest. This is also a crest. So two crests are forming what we call a cycle of a wave. A cycle. So a crest is the point. Is the point of maximum displacement above the rest position. Above the rest position on a transverse wave. On a transverse wave. So for longitudinal, we shall not find a crest. So this is limited to only a transverse wave. What about the regions? Well, actually, we were supposed to use the word regions of maximum displacement. Okay, is the region. Let us use the word region. Is the region of maximum displacement above the rest position. So the whole of this, okay, is a crest. We can talk about a point, no problem. Point of maximum displacement. Then, what about number 3, a trough? Have you ever heard of a trough? Oh, so we are going to see that a trough is the point or the region. Is the region of also maximum displacement. But below, this is below, you have to underline, below the rest position. Below the rest position. Very interesting. So, of a transverse wave, or on a transverse wave. So we shall not find a trough on a longitudinal wave. It's only limited to a transverse. It is limited to a transverse. Okay. Now let us go and talk about what we call wavelength. The general term of wavelength. Okay. So wavelength. But before talking about wavelength, we need to talk about another term which is interesting, which we are going to use in other terms, and that is in phase. In phase. Okay. In phase. So what do you mean if you say that particles are in phase?